So in general, uh, when we want to scale a database, we have very same kind of problems. So first one is that whatever database instance that we have, let it be Postgres or MySQL or MariaDB, doesn't matter. Okay, we will take any generic SQL database, for instance. So this is our SQL DB. So what happens when we have, multiple instances of our same backend doing database queries to our this single instance? So there might be case that each of this particular pod is opening a new connection for every database query that it makes. So in SQL databases, it becomes a bottleneck. So for example, in Postgres, what Postgres does is for every new connection, it spawns a new process, right? So it spawns a new process that our operating system has to, or our database management system has to overlook. So this adds a performance overhead on our existing system that is doing query planning. After that, it does all the joins and whatnot, right? So that this will add an overhead. So one of the most simplest solution is to add a connection pooler to our system in front of our database. So this is our set of, you know backend instances that want to make queries to our database, but there will lie a single process. So usually what we do is we keep the connection pooler in the same physical machine as we have our database instance baked in too. So this will be our database and this will be the same host machine. So physically these are the same machine. This will be running on the port 5143. For example, this will be running on 8180 for example. And what does this connection pooler does is it maintains, let's say, 5 connections with our database, or let's say 10 connection that is manageable. So every request that we want to make to our databases goes through this connection pool. So in a sense, connection pooler act as a load balancer. We can say not actually a load balancer, but it holds persistent connection with database, and its only task is to let the server connect and disconnect. So whatever performance overhead that this constant new connection creation was putting onto the database, it is being absorbed by this connection pool. So when Instagram, right? So when Instagram was blowing out in around 2012 to 13, uh, they scaled out to the maximum. You know, they had a single Postgres instance for up till I don't exactly remember the number, but it was something like 1 million or 10 million users. And I'm talking about uh, in 2012 13 kind of time, and they had a single Postgres instance, and the Postgres instance, they were vertically scaling it up. They were not doing any kind of, you know, uh, scaling in terms of like doing sharding and read replicas. We will discuss it later. Okay, so they were relying on a single Postgres instance, and they also face the same problem that each process will take 2 MB of their RAM, and their 64 GB of RAM was getting exhausted. 64 GB of RAM that they had was getting exhausted pretty quickly due to a lot of backend instances making the connection. So what they did, they introduced a connection rule. Okay, so this is one of the simpler solution for a pretty early scale that we might face as our app grows. So the next one is we have to identify the patterns that our database or our users are making. So when we have a database, we usually use it to do two things, which is to hold the data that we will write and access the data that we will read. So you can see we either write data or read the data. In most cases, read becomes a bottleneck in most of the system. If we take an example of any social media application like Reddit or Facebook, these social media applications are inherently read heavy applications. So whatever user that is visiting the website, it is usually only there to access the data. They are not creating data. I mean, there are a lot of people that are creating data, but the amount of people that are consuming that data will skew a lot than those who are creating. So in this particular case, we need to identify what kind of reads are coming into our application. We need to analyze those patterns. So first one is a small amount of data is being accessed. Okay, so what does it mean? So let's take an example of YouTube. We are not going to discuss about how YouTube does it. We are just going to take a naive example that something like YouTube exists for this our scenario. Okay, so in YouTube, you can we can say that there are a lot of data that is being created there is a lot of data that is being read, but only small amount of data or videos, right? So there are a lot of videos that is being uploaded by a lot of creators, but the consumer are more than the creator, and popular creators are also much more than the non-popular creator, meaning that there are only some videos that will be accessed much more than a lot of videos which will have very few views, right? So views will be less, here views will be more. So we can say that the small amount of data is being accessed in much more quantity, so that we can say that these videos are causing bottleneck in our system. So in order to tackle this, you might have heard this, that we use a cache in front of our database. So what we can do is we will have a pool of servers here, right? This is the pool of servers that we have. Then also we have our database here, our database. We also have our connection pooler here, right? So instead of, let's say this is the database that we have, right? So this is the database that I am showing you. So only small amount of data is being accessed continuously. So this data is what we call as hot hot shard of data or hot part of data. There are a lot of terminologies that these are replaced, but hot means they are being actively accessed, and the rest of the data is not being accessed, that it might cause read amplification problem in our system. So the rest of the data is not causing any kind of bottleneck, only these amount of data is causing the bottleneck. So what if we put this data into something that is sitting in front of our database? So we don't need to reach our database, our server can reach this particular store instead, to reach the data very fast, and this will be optimized for reads. So what we can do is that we can take a chunk of our database that is causing the problem and put it in the cache, so this cache can be replaced with anything that is relevant to our problem. So if we have something like a key value pair, then we can use uh, Redis, and we also have Valkey, I guess. Valkey. Yes, Valkey is another open source open source alternative to Redis. Redis is having some problems due to their change in uh, the license that owns the Reddit company. So a lot of companies are moving to Valkey. Valkey is fully open source, and I guess it is a fork of Redis. I am not sure 100%, but I have heard that as well. You can confirm it. You should also do something that I will do. If our data is something like static files, so what are static files? It could be HTML, or it could be videos, audios, anything that we might put in S3 bucket. It should be in CDN, right? It should be in CDN. So this cache can be replaced with whatever instance of cache that we want. That is best for our scenario. Okay, so this till this point we are solving like pretty much 90% of systems problem. So now next 9% that are remaining. Let's say previously what was causing this much data was causing problem. Now let's say we don't know for sure which data is being causing the problem, or all of the data in our database is being accessed equally. Let's say if we take chunk this chunk, this chunk, this chunk, this chunk, the reads on each of the chunks are same. There is no difference between, so there is no hot shard here or hot block here. Everything is hot. Our entire DB is being accessed. So in this case, what we can do? What if, what if instead of just copying the part that is, like we previously did, we copied, right? We did copy the part that was being constantly accessed. What if we just replicate the whole thing? What if we create another instance of our same database? What if we create another instance of this same database? So this will be db copy. This will be db copy. Seems pretty simple, right? So this will be our connection pooler. Connection pooler that we have here in front of our database. So you actually, we will put these two DBs on separate host machines. So this will be host 1, this will be host 2, and our servers can make a request to a load balancer. This load balancer will usually route to either of those grids. So what about writes? How will db copy will be in sync with our original database? So this is also a very interesting problem that has been solved already. So how it is solved? So the main problem is, if we try to db copy, so this is db original and this is db copy. So pretty nice solution is to ping the database for changes that are being made. Another one is whenever write happen, so this wants to write something, we firstly write into the database that is original, then again write it to the copy database. So This is also used. Uh, this approach is called as dual write, and this is used a lot in our industry. Dual write, but it is usually when migrating from one set of technology to another set of technology, not usually when we are using same instance of, you know, same. So we can do this, but it will cause one thing. We are doing two network trips. So this is first network trip and this is second network trip. So if you know, whenever you perform an operation in simple front end to back end, you make an API request. Most of the time we are waiting for our data to transfer from one machine to another machine. A lot of time is being spent transfer transferring those data, not the computation, not the rendering. The CPUs and RAMs and reads are very fast, but as we know, physics is, we can't fight physics. Data has to travel. So most of the networking is the most time consuming part of any API request that we do to another machine that is hold on the another network over the internet. So we can say that we are doubling our write speed. Actually, we are doubling our write time. We are cutting it in half, which is not very ideal, right? You are doing write to this, then you are doing write to this as well. So our database, sorry, our backend server, this is backend server is doing twice the work. And what if this DB fails? This DB is had some problem. Let's say someone spilled water on the database machine. Then what will happen? Then we will write on the database one only. What if database original goes down and the database copy comes back on? Then we are out of sync. We don't know which database to trust. So truth, whatever truth that we have in our system should be told by someone who is only telling that. So what I mean is that there should be single machine that tells the truth, single point of truth, right? Which will be in our case DB original. So how can we do this? So for this, we need to understand how a database performs an operation. Okay, we'll understand this. So whenever a database wants to write something, it at first produces something called as write ahead log. So we need to understand this. We will understand this. Okay, we will try to do write ahead log. So the name itself suggests that it is a log, means it is a book. It is a book that is being written ahead, that is being written ahead of any modification that we want to do to the data, modification that we want to do to the data. So let's say I want to either update, insert, delete, any kind of operation that modifies the data that is already exist in our system, we do write ahead log. We will call it val. Okay. So our database produces a book, a ledger of what it wants to do, so that it can do a lot of performance optimization like bulk write, and there is so much to learn about database internals which we will cover somewhere in the future, like how B plus trees work and how data is being stored into the page, and uh, it can cache those page numbers and it can write to those pages in bulk, so that it doesn't have to do disk IO. So disk IO is uh, slow compared to the RAM IO that is fast. Okay, so not moving off topic. So this write ahead log is being produced and stored to the disk as well before doing the actual modification or execution part of any modification query. So as we said, the insertion or up, updation or deletion, these are pretty much the modification queries that happen. So what we want to do is copy this write ahead log. So we know that write ahead log will have everything in detail written about what operation to do. If we give this book to the copy database, it can actually reproduce this original database from start to end. If we have everything written in our val, then we can reproduce our database, right? So this is the simple formula behind the read replicas that we are currently discussing. So this is called as read replication. So we are having a replica of our database so that we can repurpose that or purpose or use that replicated database for reads. So this is what we want to do. What we want to do is, whenever our original database produces a val, we will transfer this val to the copy database copy, and it will also have the same wall. It will also have the same val, right? And the whatever operations that whatever computation that happens before generating the val, the copy database doesn't have to do it, right? It just has to execute that val, and after execution the val, we will insert it or update or delete or do whatever operation our write ahead log tells us to do. And for achieving this, we usually use something called as CDC, which is change data capture. On data change, or sorry, capture data change or change data capture, I don't remember actually, but the main point is that whenever data change happen, we capture that data change. So whenever val changes, we capture that change and send it over to the network to our copy database. So we had single copy database. What I can do now is have another database. So copy database. This is another copy database. I will also send the val to this database as well. So now I have two replicas, one primary data which produces the val, right? Whatever operations that are being done by our these servers, these servers is being done on this primary database, and our primary database generates the val. We send our val to different replicated databases. Fun fact, OpenAI uses 50 read replicas of Postgres. Pretty amazing, right? I think they might have increased from 50 to something, I don't know, 60, 65, 70, 75. But a couple months back, they released the article about how they achieved the scale that they provide with 50 read replicas. Okay, so this was about read replicas. There are a lot of database native extensions around read replication. We can check them, one of them out, I guess. So read replication for Postgres extension. PG Logical. So you can, yes, PG pool. I remember this. So PG pool is, it will do everything. The connection pooling, the high availability. High availability means, okay. Let just a minute. Just a minute. I'm sorry. Okay. Yes. PG pool. So for Postgres, PG pool will solve like every problem, that connection pooling, load balancing, high availability. So high availability usually refers to, read replica. You can read about it more in the documentation. Always refer the latest. Okay, so this is how we will solve the read replication problem. So now, what if it's okay about reads? What if our this single database can't keep up with how much val it is producing, and it is not getting time to execute that one? Then what? We have 50, let's say, two replicated databases, but our val is being generated, but the amount that, or we can say, the amount of val that is being generated is not being executed by our database so that we can keep up with the generation. So let's say we can execute 10 val per second, and our uh, reads, oh sorry, our writes are amplified at that rate that we are generating 15 vals per second. So each second we are having extra 5 vals that we can't execute. So this is a problem. So this is a problem, right? So we also know that our database will look like something like this, right? Our database will look like something like this, and and our database will have a lot of data that is being put in chunks. Okay. So for example, let's take a users table. Okay, we'll take a users table. Users table. So let's say I have 1 million users, just for the sake of it. Okay, so I have two user sets. We are separating them logically. Okay, we have not done anything in our system that separates them. Okay, so we have a single users table, and all of these 1 million are in that table. But we can, for our understanding, we can split these users into two parts. The first one being from first to 500k and 500k1 to 1 million, right? So now, instead of just writing to db1, which was original db, which was producing 15 vals per second, and our database was able to only execute these 10 vals. What if we split it into two separate databases so that we can have 20 vals execution per second? Right, we have two separate database entities. So these 10, this can database instance can execute 10 vals. This database instance can execute 10 vals. So this is called as sharding. What we have done is we have created a shard of our database. So there is also something called as partitioning. And if we uh, go to the internet, sharding versus partitioning. So partitioning divides the large database into small pieces within a single database server. Sharding takes this a step further by dividing those partition chunks across individual database servers. So what does partitioning do is we will have a single database. We'll have a single database. Okay, we'll have a single database. Inside that, sorry, yes, a single database management system or cluster, whatever we call it. So it will live on the same node or same physical server, but it will have two separate databases inside that thing. But our single node can do so much, right? Our single node can't do much more due to the physical constraint that it has to follow. So partitioning is also good way to solve this right amplification problem, but usually it is not enough when we reach that scale. So we have to go to sharding, we have to split horizontally, we have to scale horizontally, right? We have to have that peace of mind of having enough compute, enough physical resources. But sharding usually causes a lot of problem if not done correctly. Like we have query planner, right? Every database will have a query planner. So inherently, the SQL, whatever we call it, is inherently declared. Tell the database what we want. So we just declare that I want to select ID and name from employee, right? From employee. How to get this data? How to execute this particular query onto the database is being done by the query planner, right? But if we have two separate nodes, then we can't actually use the benefit of query planner wholly, right? And what if some of the data lives in first partition, some of the data lives in second partition? Then we have to do uh, two network calls to actually join the data. We have to do what query planner does for us. We have to maintain that system. But usually we don't shard our own, we don't actually shard. There are a lot of managed service like Neki for Postgres by PlantScale. This is not sponsored, by the way. I love PlantScale. I use it. PlantScale is pretty fast uh, and good as well. Uh, and they also have something for MySQL as well. They actually started with MySQL first, and they have released the Neki recently, I guess. Not Nikio, it's Neki. So we can go to the PlantScale. You can say the PlantScale blog is the first one. PlantScale is the database company. I love it. PlantScale, MySQL, Shark. Hmm. Yes, Vitess. Vitess is actually open source clustering system, which is developed by YouTube actually, but uh, how you execute it on the you know physical hardware level, we have to admire PlantScale to how they did it. Okay, there might be another providers that do it for us, but I know of PlantScale only. So this is how usually you know the solving of scale issue around database is being handled. uh, Also there are a lot of nuances. For each case we have to slightly make adjustment to our approach. uh, for example, let's take this example. Let me go here. Yes, so this write ahead law. uh, so actually, the write ahead lock that is generated, it is deleted after some time. We can't just keep the whole book from start to end. Right? We need to delete it. We need to delete the val that is being generated. So there is also problem of network failure. So let's say our copy database fails to get the wall that was generated by our original database, and only our copy one database received. So in this case, our copy database is out of sync. It is not having the actual data that our original database have. In this scenario, we have two options. We can either provide stale data to our users, or we can just be unavailable to user. We can give 503 or whatever 500 error, right? Service not available or internal server or whatever. So you might say that what if our server database is out of sync, then we delete it from our set of, right? We remove it from whatever reads that are coming through, we remove it from the load balancer. In case of Postgres, it will be PG pool usually, or PG bouncer, right? So we remove from the pool of databases, but let's say every second there are 25k requests per second, and each database can only handle 10k reads per second. So the first one is at the fullest, the second one is at the fullest. We have 5k requests that are pending. So these 5k requests either can be dropped, or if routed to this or this database, then both database might also go down, right? If we decide to remove this, right? So this is the problem, or this is the trade-off that might we have to face. So instead of routing those 5k requests again to available databases, we drop them. We become unavailable to the user. Our database becomes unavailable to the user, right? Or we can be available to the user, but we can be inconsistent. We can be inconsistent. What we can do? We can be inconsistent. We are highly available. We are available, but we are also not consistent. It means that we are serving the stale data to the user because we don't have the updated val in our copydb. So this is also a trade-off that we are making. We are either being highly available or being highly consistent. We want to show the only data that is latest, or we might drop the requests. Also, there might be the case that where our original database itself might go down. This can happen. So what to do now? So actually the PG pool handles this. The PG pool will uh, route the request for write directly to either of the database. So this copy DB actually becomes our primary database. This will become our primary database. I know the diagram has become a non-beautiful. You understood the thought process with the trade-offs that comes when building, uh, you know, databases for scale. I continue to provide some amount of information as time goes by, as I learn things. So this to understand everything, it took me like 3 to 4 months. So I was able to understand this. I mean, I have read about this like 2 years back. So actually, the information sharing is done. So you can drop off. I will be ranting or yapping for some time. So this was like the first time I heard about Valve was like 9 to 10 months ago, uh, and about partitioning, I guess I learned it during my college lectures. The partitioning replication, that was the dual write problem. I heard it from one of my roommates during uh, my internship. He told me how he uh, migrated from MySQL to MongoDB by using dual writes for migrating the databases. Pretty much everything is very interesting in computer science, especially the database and operating system. I hope you learned something new. Thank you for giving 1 hour of your time if you are here. So yeah, see you again in the next session. Goodbye. Have a wonderful day. Jai Hind. Jai Bharat.